So once again, we're asked to factor a polynomial completely. The completely is just your indication that you may not have just one step of factoring. You may have to combine a few different ways to factor. So let's take a look and see how these three examples are going to work out. So I always want to start with a greatest common factor. So taking a look at x to the fourth minus 121, there isn't one. There's nothing those have in common. And so at that point I want to figure out, well, what else can I do? And again, this is where your flowchart is going to be really handy because it kind of organizes your different options depending on how many terms you have. The problem has two terms in it, so there's really only two things I can try. I could try difference of two squares or sum or difference of two cubes. Well, if I try to do the cube root of x to the fourth or the cube root of 121, it's not going to work out very well. But if I do the square root, I will be able to get some answers that are not in it or that are not decimals. So let's actually do this as the difference of two squares. Even though it's x to the fourth, watch how we can still work this problem out. So with difference of two squares, recall that we get two parentheses, and then it comes down to square roots. So the square root of x to the fourth is x squared. So that's in the front spot, and the square root of 121 is just 11, so that goes in the back. The only difference is that one parenthesis is plus and one parenthesis is minus. So at this point you want to try to factor again because you haven't got down to x to the first power yet. If you get down to x to the first, you know you're done. So we want to try to factor again if we can. Since we have x squared, we can try difference of two squares a second time. However, the first parenthesis has a plus sign in it, so it's not the difference of two squares, so we won't be able to factor that piece anymore, so that'll be done for sure. The second parenthesis is a difference of two squares, but if you try to take the square root of 11, it's going to come up as something irrational, so it's not a perfect square. So actually this time, that problem is factored all the way. Sometimes we can't get down to x to the first power. That's been factored as much as we can. Compare that to this next example, because at first glance it looks like it's very similar, but watch the subtle difference at the end of this problem. So once again, it is difference of two squares, and there's not a greatest common factor. So I'm going to take the square root of x to the fourth and the square root of 81, and just like last time, the square root of x to the fourth is x squared. So that goes in the front. There we go. And the square root of 81 is 9. And the only difference is 1 is plus and 1 is minus. And so you may be thinking, okay, I get it. It's the same thing we just did. But watch where this one's a little bit different. Once again, that first parenthesis is not factorable because there's a plus sign in it. So that first parenthesis is definitely done. However, the second parenthesis is a difference, and 9 is a perfect square. So we can actually do difference of two squares again, and in fact we have to do it a second time. So the way that that's going to factor, that would factor into x plus 3 and x minus 3. So this time we could factor a second time. Don't forget that first parenthesis though, that cannot be factored. And a lot of people, it drives them crazy because they're like, well, why did you factor one side but not the other? The x plus 9 is not the difference of two squares, and we don't have anything called the sum of two squares. So this time we can get down to three parentheses. All right, and let's take a look at one more. This one, I'm sure you're sick of difference of two squares by this point. This final one is not the difference of two squares. Look, there's three terms in it, but it's to the 8th power. Ooh, this should be fun. Start out with greatest common factor. This time there is one. Everything's divisible by 2, and they all have a p squared in common. So I'm going to factor out a 2p squared, leaving me with p to the 6th plus 5p to the 3rd, and then plus 6. Okay, we have a trinomial, and there's just a 1 in front. What's unusual, though, is our exponents. And we're used to seeing trinomials that are, p squared plus 5p plus 6. Well, the good news is this. We're going to pretend right now. We're going to go to imagination land and pretend this is just a normal polynomial, a normal trinomial. I call it the pretending method for factoring. It works as long as that highest power is even, and as long as that next power is half of your highest power. We're going to pretend. So pretending this is a normal trinomial, what I want to do is I want to figure out what multiplies to 6 and what adds up to 5. I can do that because there's a 1 in front. If there wasn't, I would need to pretend and use the box method though. So the two numbers that do that, that's actually pretty easy. The two numbers that multiply to 6 but add up to 5 are going to be 3 and 2. So I'll end with a plus 3 and a plus 2. And then like we've done before, we'd have a p in the front. Now here's the thing, we were pretending, and so at some point we have to come back to reality. The reason we put those p's in front before is because p times p got us p squared, but this time we need to get to p to the 6th power. And so what those exponents need to be are actually p to the third. P to the third times p to the third would get us p to the sixth power. Or one way to remember it, it's just going to be that middle exponent always. So we'll pretend to get this one factored, but then before we finish it, we have to come back to reality and put those correct exponents on it. Don't forget your GCF, that's going to carry down in the front, so 2p squared. Now before we circle it and say we're done, we should try to factor those parentheses again. They're p to the third power, which means I can try sum or difference of two cubes. They're both sums. I mean, with cubes, it doesn't matter if it's sum or difference, and they're p to the third power. So taking a look at the numbers, though, the cube root of 3 is nothing rational, so that part won't work. The cube root of 2, also not rational. Neither 3 nor 2 are perfect cubes, so I guess that's good news for us, those of you that are tired of factoring. This has been factored all the way. I don't have sum of two cubes, so I cannot factor any further. Remember, if you want to check any of these, even these ones to really high powers, you can check them the same way we've been checking. Graph your answer as y1, graph the original problem as y2, and just check your graphs. If they're the exact same thing, you know you've factored correctly.